Okay. It's the lowest attendance we've had so far. Hopefully more people will show up. Okay, so we're in the middle of proving the Morse index theorem. I'll remind you what the Morse index theorem says. We're going to finish that for sure today. And then we have 3 more lectures. And I decided that I'll cover chapter 12, which is about Priceman's theorem, which is telling you something about the fundamental group of a Riemannian manifold if the curvature is everywhere negative. So that's a nice mix of both the geometry and the topology and some algebra. And that might not take us 3 full lectures, or it might. If we finish somewhere in the middle of the final lecture, we'll stop early because there's no time to do anything from chapter 13. And chapter 13, you can tell he was tired of writing the book, and it's the sort of poorest written chapter. There's very large gaps of details and lots of obvious typos. So you can read it, at your own risk after the course, but it's poorly written. Anyway, so let me remind you what the Morse index theorem says. So if we have a geodesic, non-constant geodesic segment on M, then we look at the space of piecewise smooth vector fields along this geodesic, which vanish at the 2 endpoints. And we look at this symmetric bilinear form on V. And this is exactly the second variation of energy for a proper variation of the geodesic. It's a symmetric bilinear form, equivalently a quadratic form. And the Morse index theorem says that the index of this symmetric bilinear form is finite, which was not obvious because it's on an infinite dimensional space. And that the value of the index is the sum counted with multiplicities of all the interior conjugate points of gamma. So if there's some t between 0 and a where gamma of t is conjugate to gamma of 0, then that has some multiplicity, which is the dimension of the kernel of the exponential map at that point. And then remember, the index is the size of the maximal negative definite subspace, the dimension of the largest negative definite subspace. So we did this last time. We proved this, that the index is finite. And we also showed, because it's going to come up again today, showed that the radical of IA is equal to the Jacobi fields along gamma, which lie in V. So in other words, they have to vanish at the 2 endpoints. Okay, that's going to come up. So that what we need to do now is to show that the index, the value of the index is equal to the sum of these interior conjugate points counted with multiplicity. So let's introduce some notation. So let's let t be some time between 0 and a. We'll let gamma sub t denote gamma restricted to 0t. So we don't have to keep writing the restriction. And let it be the index form of gamma t. Okay, so the fact that the index is finite, right? This was for any a, right? We just said gamma from 0 to a is some geodesic. So we already know that the index of it is finite for any t, and let I be the function from 0a to the non-negative non-negative integers. These include 0, given by I of t is the index of it. Okay, this is a non-negative integer. So we want to study properties of this integer valued function. And more notation, let's let Vt be the piecewise smooth vector fields along gamma t, which vanish at the endpoints. And so in particular, the radical of it is equal to the Jacobi fields along gamma t, which lie in VT. Right? It's exactly this result in yellow here from last time, just applied to the restriction to 0t. And also, we saw that it was convenient to introduce, for given this geodesic, a subdivision of the domain with the property that if we restricted that geodesic to each of these closed subintervals of the subdivision, it was minimizing and had no conjugate points. So recall, we had chosen a regular subdivision. De Carmo calls it normal, but I didn't want to do that because it confuses with orthogonality. A regular subdivision, T naught, T1, Tn minus 1, Tn, of this interval, such that gamma restricted to Tk minus 1, Tk is minimizing with no conjugate points. And we did that by covering gamma by a finite number of totally normal neighborhoods and choosing the points appropriately. So when I say here no conjugate points, I want to emphasize again, I said this last time, the restriction of gamma to here is a geodesic on here. This geodesic has no conjugate points on it, which means that there's no time between Tk minus 1 to Tk where gamma of that time is conjugate along this geodesic to gamma at Tk minus 1. That means there's no Jacobi field along this geodesic, non-trivial Jacobi field along this geodesic, which vanishes at the two endpoints. Okay. So in particular, the first thing to observe using this subdivision, if T is less than T1, less than or equal to T1, then IT of VV is the second second derivative at time 0 for some variation for any proper variation of gamma t with variation vector field V. Gamma restricted to 0 T1 with variation vector field V. Remember, any vector field along any piecewise vector field along a geodesic is the variation vector field of some variation. And if that vector field vanishes at the two endpoints, then it's a proper variation. And this IT, no, I want to do gamma from 0 to T. That's right. So it's minimizing on 0 T1. So it's certainly minimizing on 0 T for any T less than or equal to T1. And therefore, we know that the second derivative, the second variation formula is non-negative. Sorry, I forgot to write non-negative. Okay, so there's no vectors you can plug in to IT if T is less than T1, which will give you something negative. So the index of T is 0 if T is between 0 and T1. Okay, so for sufficiently small T, the index function I of T is 0. Okay, and that's because for a small enough piece, it's going to be minimized. Now we want to see what happens to this function little I of T as we vary T. So we're going to prove a series of claims. Claim number 1, I guess this is claim 0, but claim number 1, I is non-decreasing. So i.e. what I mean, that is, if T bar is bigger than T, then I of t bar is greater than or equal to I of t. So why is this true? This is easy. Proof of claim one. So I of t is the index of I sub t. So there exists a subspace U in VT with the dimension of U equals I of t, on which I sub t is negative definite. That's what it means. And in fact, there's no larger subspace on which it's negative definite. So let V be in this space script U and extend it to some, this is just notation, right? This is no closure or anything, to some vector field V bar on V T bar by defining V bar at T at S is 0 for all S in T to T bar. Okay, remember, this guy was in here, and this is a subspace of VT. And what does that mean? It means it's piecewise smooth on gamma up to T, and it vanishes at 0 and at T. So then I just extended by 0. Since it vanished at T, this is still piecewise smooth. V bar is piecewise smooth along gamma T bar. So V bar is in script V T bar. Okay, and now let's compute I T bar of V bar V bar. That's going to be the integral from 0 to T bar V bar prime minus R V bar gamma prime V bar. And this thing is, I can go 0 to T and then T to T bar. And from T to T bar, V bar is identically 0. So this is the same as 0 to T V prime minus R of V gamma prime V, which is IT of V. Okay, and that's less than 0 because, so I need V to be non-zero. What do I want to prove? I want to prove that I of T bar is at least I of T. Well, if I of T was 0, then this is definitely true. So I can assume, so this is trivial if I of T is 0. So assume I of T is positive, it's integer valued. That means there is something that means this space U is not 0. So there is something non-zero in there. And because IT is negative definite on U, this is strictly negative. So, so IT bar of V bar is less than 0 for all V bar constructed from V in U. And we can see that this map that takes V to V bar is linear and injective. Hence, the dimension, the index, this is the index of I T bar, is the dimension of the largest negative definite subspace. Well, it's going to be at least equal to the dimension of U, because for everything in U here, I find a vector in script V sub T bar, which makes this thing negative, and that's equal to I of T. Okay, so that's the proof of claim 1. This function is integer valued, non-negative integer value. It starts out, at least for some positive amount of time, being identically 0, and it's non-decreasing. So there are two more properties we need to prove about this function, but we need to introduce. Okay, good. I still have this here. So to consider the remaining properties of I of t, of I, so recall, observe that I of t is defined to be the index of it is independent of the regular subdivision here. Subdivision 0 is t naught dot dot dot. Right? Because we introduced this subdivision to be able to prove last time that the index is finite, and now to show that it starts out at 0. But the definition of the index has nothing to do with any regular subdivision. So for fixed t, let's say in 0a, we can, without loss of generality, choose the subdivision so that t is not one of these special points for some j. And we want it to be, j at least one. So, I mean, how do we do that? Our initial, if t is not a subdivision point, there's nothing to do. But if it was a subdivision point, let's say this one was tj and then this one was tj plus 1, I can just choose another point in here. It's still going to be true that this will be minimizing and have no conjugate points here, and choose another point in here. That's still going to be true for all of these three segments. So by refining if necessary. Okay, so now we're going to work. We're going to study I of t for this t, an interior point, and we can assume that our subdivision avoids it. So from last time, we know that I of t, which is the index of it, equals the index of the restriction of it to what we called v minus t. So I was doing that before on last class for the whole interval from 0 to a. Now I'm doing for 0 to t. It's the same thing. And this is the piecewise smooth vector fields v along gamma t, which remember was gamma restricted to 0 t, such that v restricted to tk minus 1 tk for k equals 1 up to j minus 1, and v restricted to tk to t j minus 1 up to t are Jacobi fields. Along the respective, along their geodesics. What do I mean? This is a Jacobi field along gamma restricted to that, and this is a Jacobi field along gamma restricted to this. Right? That was the definition of this space V minus. It was a finite dimensional space, and we proved last class, after a lot of hard work, that that if you restricted IT to this subspace, it had finite index, and that the index was equal to the index of IT on the whole VT. Okay. But given a vector in VT minus that has these properties, it's uniquely determined by its values V at T1 up to V at Tj minus 1. Sorry, I guess yeah, that's right. So these are at the points gamma T1 up to gamma of Tj. And why is Tj minus 1? Why is this? Because the subdivision was chosen so that for each of these restrictions, these closed subintervals, all of these, the geodesic is minimizing with no conjugate points. And we know that if a geodesic has no conjugate points, then if you prescribe the two boundary values, there is a unique Jacobi field with those boundary values. So this is since gamma restricted to each tk minus 1 to tk, k equals 1 up to j minus 1, and gamma restricted to tj minus 1 up to t have no conjugate points along themselves. And what I mean here is that we're thinking of each of these as its own geodesic, and it has no conjugate points in this interval to its initial point. So a Jacobi field along those geodesics is uniquely determined, exists and is uniquely determined given prescribed boundary values. That was something we proved at the end of chapter 5. Okay, so in other words, the map, oh, and so why do I only need to define these? That's because, so note that V at 0 and V at T have to be 0 because it's in here, right? This is piecewise smooth vector fields that vanish at the two endpoints. So those are prescribed for sure because it's in here. And then if we just prescribe these guys, there is such a V and it's unique. So in other words, the map, let's call it FT, which goes from VT minus to T gamma T1 M plus T gamma Tj minus 1 M, that takes V and sends it to V of T1 up to V of Tj minus 1, is a linear isomorphism. Okay, the fact that the Jacobi field exists and is uniquely determined by the boundary values tells you that this is a bijection, and it's obviously linear. Okay, so let's call this right-hand side Sj minus 1. So the dimension of Sj minus 1 is, each of these is dimension n, so it's n times j minus 1. Okay, so we're saying that for any t between Tj minus 1 and Tj, this space, which is determining the index of IT, because the index of IT is the same as the index of IT restricted to this, all of those things can be identified with this fixed vector space that doesn't depend on T, as long as T is in between Tj minus 1 and Tj. So let's write that over here. So hence, for all T in Tj minus 1 up to Tj, the space Vt minus can be identified with the fixed vector space Sj minus 1, which is independent of T. Okay, and hence for all t between tj minus 1 and tj, we can regard the restriction of it to vt minus as a quadratic form on sj minus 1. Okay, so really what we have, so we have a family it t in this interval of quadratic forms on a fixed vector space. And you see this is a big simplification, right? Because the problem before was that for any t, it was a quadratic form on some different space. Okay. So we have 3 more claims to prove, and then we'll be done. So claim number 2, claim number 1 was that I was non-decreasing, right? So I restricted to some small epsilon is identically 0, and I is non-decreasing. Now, the second claim is as a quadratic form on this fixed sj minus 1 for t in tj minus 1 to tj, it is continuous in t. Okay, so we're restricting ourselves to this interval, and via this identification, this isomorphism, we just have a 1-parameter family of quadratic forms on a fixed finite dimensional vector space. And we're saying that this family of quadratic forms is varying continuously. So what do we mean by this? So let V be in Sj minus 1, then T goes to IT of VV is a real number here. This is continuous on Tj minus 1 to Tj. This is what we want to show. We want to show that for any V, this map is continuous. Okay, so let's write it out. So V is in Sj minus 1. IT of VV, remember, I'm being a little bit sloppy with abusive notation here. When I write it like this as a quadratic form on Sj minus 1, I really mean I'm taking IT applied to Ft inverse of V. Right? Remember, Ft goes from Vt minus to Sj minus 1 as this linear isomorphism. And that's a little v, right? Just for simplified notation, let's let capital V be Ft inverse of little v. So we get that IT of little v, this is equal to 0 to t. Well, we had this alternative formula for the index form. We did this last time. We can rewrite it by integration by parts into a part which involves the Jacobi equation. Oh, let's call this du, because I'm integrating up to t, minus the sum from L equals 1 up to j minus 1, v prime t L plus minus v prime t L minus VTL. And we want to see how this depends on t. V is fixed now. Little v is fixed. But of course, capital V, even though little v is fixed, capital V depends on t. This depends on t. But we do know that because capital V is in script VT minus, capital V, which is FT inverse of little v, is in VT minus. So V is a Jacobi field, or let's say satisfies Jacobi equation for all t not equal to a tj, to a ti, right? Because it is a Jacobi field. The point is that V double prime is not well defined along the whole gamma, right? But if I restrict to some interval tk minus 1 up to tk, then the definition of this space is that V restricts to a Jacobi field along that geodesic. So it satisfies the Jacobi equation on that interval. So V double prime doesn't make sense at these jump points, but everywhere in between, V satisfies this equation. So this is always 0, okay? Also, if t is in tj minus 1 up to tj, then V prime TL plus or minus is unchanged, is independent of t, for L equals 1 up to j minus up to, well, let's just write them slowly. Which ones are independent? V prime T1 plus or minus up to V prime T j minus 2 plus or minus, and V prime Tj minus 1 minus. These are independent. So only V prime Tj minus 1 plus changes. So what am I trying to say here? This isomorphism, you know, to know what you get when you apply, you take a fixed vector in here and you apply FT inverse to go in here, you prescribe these values here, okay? If I'm varying t from tj minus 1 to tj, then the only thing that changes, so what do I have? I have a Jacobi field with prescribed values at these points, okay? I'm not changing these points because I'm always in Sj. So the definition, this map FT inverse goes from Sj minus 1 to Vt minus. As long as t is staying in the interval between tj minus 1 and tj, the first, so here's t1 up to tj minus 1, and then this is t, and tj is up here, okay? So I'm not changing the values of, I'm always in this same point. Little v is always the same point in Sj minus 1. So these things are fixed, which means the values of my Jacobi field here are fixed at all of these points, okay? So I've fixed the value here and here. Then I know what the Jacobi field is here. I fixed it at T2. I know what the Jacobi field is here. I've even fixed it at Tj minus 1. The only thing that's changing is this point T is moving, okay? So I need, for different points T, I need the Jacobi field, the unique Jacobi field, which has this given value at Tj minus 1 and which vanishes at T. But that T is moving, okay? So the only thing that's going to change is the derivative of V prime at Tj minus 1 from the left, so the plus. This is the only thing that changes. Okay, so in this description of IT for different T's, this is some constant independent of T minus V prime Tj minus 1 plus V Tj minus 1. Okay, and this is also constant. This changes. Okay, and now here, which is not unusual for him to come, was very, very vague. So he says that this is obviously, he doesn't even put in all these details, right? He just says from this formula, it's obvious that this thing is continuous in T. Not at all obvious. So then the idea is one needs to show that we have continuous dependence on boundary values in the following sense. Okay, so let's say we look at gamma restricted to Tj minus 1 Tj. This is some geodesic. And we know that the Jacobi fields here, because it's got no conjugate points, are going to be uniquely determined. They exist and are unique given the boundary data. So V of Tj minus 1 is fixed. Okay, and then V is uniquely determined by either V of Tj, because it's got no conjugate points, or by the initial value of the velocity, right? V prime. And this so the point is there's only one V given this is fixed. There's only one V, there is one and only one given either this or this. Okay, and it depends smoothly on the initial conditions. Depends smoothly on initial conditions, but this is not quite what we want. Our solution is determined by the fact that it vanishes at some time t. But our solution is determined by the condition that V of t equals 0 for t in Tj minus 1 Tj. So rather than prescribing, an initial derivative or a boundary condition at Tj, we're prescribing the value at some point t in the middle, and we're moving that. So you need to check the solution depends continuously on t. Now, I didn't actually do this, so I'm going to let you do it on your own. If you find a very, very quick argument, I would like to see it. I'm sure it's true, but there's definitely some steps here that he skipped. Okay, so that's the end of claim 2. So I'm going to keep writing what we've shown. We've shown now that IT on Sj minus 1 is continuous in T in here. That's what we have so far. Claim number 3 says that the function little I, the index function, is continuous from the left. Claim number 3, there exists epsilon sufficiently small such that I of t minus epsilon, oh no, sorry. Yeah, that's right. For all epsilon sufficiently small, I of t minus epsilon equals I of t. Okay, so I is continuous from the left. We know it's non-negative integer valued, but it could jump, right? And what we're saying is that whatever value it takes at t, then as long as you don't move too far away to the left, it's going to take the same value. Okay? Constant to the left for a small time. So the proof, well, we already know it's non-decreasing. Since I is non-decreasing, we know that I of t minus epsilon is at most I of t for all epsilon such that t minus epsilon is at least 0. Remember, t is bigger than 0 now. Otherwise, this doesn't make sense, right, for times that are less than 0. So this is fine. We need to show the opposite inequality. We need to show that I of t plus epsilon is at least I of t for epsilon sufficiently small. Okay. Let S bar in Sj minus 1 be a subspace such that IT is negative definite on S bar with the dimension of S bar equals I of t. We know that because that's the index. Typo in my notes. And here's where we use claim 2. If you have a quadratic form, a family of quadratic forms on a fixed vector space, which is varying continuously with this parameter, then the notion of being positive definite or negative definite is an open condition. So since IT is negative definite on S bar, by continuity of IT on Sj minus 1, this is claim number 2, there exists some epsilon positive such that IT minus epsilon, for all epsilon sufficiently small, I of t minus epsilon is still negative definite on S bar. Okay, so being positive definite, being a negative definite or positive definite quadratic form on a finite dimensional space is an open condition. Okay, so as long as we vary t, and I don't have to vary to the left. I can also vary to the right, and it'll still be true. But varying to the right is not going to give me any useful information here. So that means that this subspace, I of t is negative definite on this subspace. So as long as t is close enough, as long as I move to something sufficiently close to t, then the new quadratic form will still be negative definite on this. So I of t minus epsilon, which is the index of I t minus epsilon, is going to be at least the dimension of S bar, which is I of t. Okay, that gives me the opposite inequality. And then I get the conclusion. You see, it's also true that if epsilon is sufficiently small, then I of t plus epsilon will also be greater than this. But that doesn't help me, right? Because I already knew that by the non-decreasingness. Okay, so property claim 3 is for all epsilon sufficiently small, I of t minus epsilon equals I of t. And now we're ready for the last part. You'll notice we haven't really used anything deep yet. This is all just sort of calculus and linear algebra. We haven't used the geometry yet, and that's when it's going to come here. Frame number 4. Let's let d of t be the dimension of the radical of I of t, which is equal to the multiplicity of gamma of t as a conjugate point to gamma of 0. And that's because, this is not the claim yet, because the radical of I of t is equal to the Jacobi fields along gamma t vanishing at the endpoints. That was from last lecture. We described the radical of the index form as a space of Jacobi fields which vanished at the endpoints. So how big is that space? Well, it's the space of Jacobi fields vanishing at the two endpoints. That's exactly, if there is such a non-zero Jacobi field, that means gamma of t is conjugate to gamma of 0. And how many such Jacobi fields are there? That's exactly the multiplicity of gamma of t as a conjugate point to gamma of 0.
Question.
Yeah.
So what's the kind of geometric intuition for having a multiplicity greater than 1? I mean, is there like like a simple model of it where, yeah.
The geometric intuition,
like for a
polynomial,
like for polynomials, there's sort of an intuition for multiple roots, and if you perturb them slightly, you get
so I think
distinct roots. I mean, is there something like that?
There is something like that. So what does it mean to have a Jacobi field? What does it mean to have a conjugate point? It means there exists some non-trivial Jacobi field which vanishes at those 2 points. Okay, and you can show from there that remember what is a Jacobi field? Given a Jacobi field, you can essentially construct. Well, let me say what it means. So here's a picture. Gamma of 0, let's say gamma of a. Let's say this is conjugate to here. Right? That means there exists some Jacobi field which is non-trivial and which vanishes at these 2 endpoints. Okay. Then you can construct a variation using that Jacobi field, a proper variation. So you get a family of curves joining these endpoints. But actually, you can do that with any vector field, any piecewise smooth vector field that vanishes at the 2 endpoints. But when this is a Jacobi field, then you can almost get. I'm cheating here a little bit, and I'm not going to go through the details because this wasn't the point. I wasn't going to do this in the course, but I'll just say it as an answer to the question. If V is a Jacobi field along gamma with V of 0 equals V of a equals 0, then you can almost construct a family, a variation, a proper variation of gamma through geodesics. Right, so we want all of these things to be geodesics also. It doesn't quite work, and I'm not explaining how to do this. You can look this up, but the point is, because it's a Jacobi field, you can almost do it. You actually do get a family of geodesics, but they don't quite end up at gamma of a. They're close. They're very close to being at gamma of a. So if you expand it in a Taylor series, then they miss closing up to here just sort of by one order, right? So that you can get a family of geodesics starting at gamma of 0, and they almost go to gamma of a. And then if the conjugate point has a higher multiplicity, you can get that many different independent such variations, right? So it basically says, it's not quite exactly this, but it basically says how many different ways, linearly independent ways, can you find essentially a family of geodesics joining those 2 endpoints. Okay, that's something somewhat geometric, but it's not precise because you can't actually get it to close up. So if you look up conjugate points on Wikipedia or something, it'll explain this a little bit better than what I'm doing. Okay.
Thanks.
Yeah. Yes, thank you. Thank you. Okay, so now we're ready for claim number 4, which is the interesting geometry. I've defined d of t. Claim number 4 says if epsilon is sufficiently small, then I of t plus epsilon equals I of t plus d of t. Okay, so this says that I jumps at each t such that gamma of t is conjugate to gamma of 0, and it jumps by an amount d of t, which is the multiplicity of gamma of t as a conjugate point. Okay, so it's not continuous from the right. So it's not continuous from the right. It looks like something like this, right? It's a non-decreasing integer valued function which starts out at 0, and at some times it jumps by some integer amount and then continues. Okay, so how do we prove this? Again, we're going to prove that each side is less than or equal to the other side. So first, we show that I of t plus epsilon is less than or equal to I of t plus d of t. And this again will use the continuity of I with respect to t. So since the dimension of Sj minus 1 is n times j minus 1, it is positive definite on a space P, subspace, of dimension n j minus 1 minus I of t minus d of t, because this is the maximal negative definite, and this is the radical, the space on which it's degenerate. Okay, so for finite, we're on a finite dimensional space now, and for a finite dimensional space, if you have a symmetric bilinear form, then there's the number of positive, the maximal number of positive, the maximal dimension of a positive definite space, the maximal dimension of a negative definite space, and then there's the dimension of the radical. So we have P plus Q plus R is the dimension of Sj minus 1. And this is just a fact about symmetric bilinear forms. I mentioned this when we did our review of symmetric bilinear forms. So because Q is I of t and R is d of t, that means there is a subspace P of this dimension, right? This dimension minus Q minus R, on which it's positive definite. But now we use claim number 2 again, the continuity, to say that as long as we don't change t too much, it'll still be positive definite on P. So again, by continuity of IT with respect to t, let's see, on Sj minus 1 with respect to t, for epsilon sufficiently small, IT plus epsilon will still be positive definite on P. Right? This is just like we did in claim 3. So hence, the index of IT plus epsilon, well, that can't be, that's the largest number of negative definite space, right? It's the value of the dimension of the largest negative definite subspace. Well, it can't be any more than the dimension of the space minus the dimension of the space on which it's positive. Right? So this is saying, basically, I want to write the dimension of Sj minus 1 is going to be the radical, the new radical plus the new positive and the new negative index, right? I've changed from t to t plus epsilon. This is with respect to t plus epsilon. And all I'm saying is that the q tilde is equal to, this is at least 0. So the q tilde is p tilde plus q tilde is less than or equal to n times j minus 1. Because we don't know what happened to r tilde, but we know that these guys have to add up to the dimension. These guys plus this is the dimension. So the new positive, the new negative one is at most the dimension of the space minus this guy, because I t plus epsilon is positive definite on P. So the new maximal dimension of positive definite space is at least this. Okay. So, and then this becomes I of t plus d of t. So we've shown that I of t plus epsilon for epsilon small enough is this, for epsilon sufficiently small. We need to show that we have the opposite inequality for epsilon sufficiently small. Okay, so now is where the non-trivial geometric input comes in. Up to now, it's just been calculus and linear algebra. So we do this. We're going to use the index lemma, which was the tool we used to prove the Rauch comparison theorem. So let's let V be in Sj minus 1. Type on my notes. With V of Tj minus 1 not equal to 0, so that the restriction is not to Tj is not identically 0, right? Because remember, I guess I'm identifying, this guy is a fixed vector space. Little t is varying between Tj minus 1 and Tj, but these values are if this, okay, what am I saying here? If this was 0, right, it doesn't matter which t I look at. V is ft inverse of little v. Let's call this little v. Okay, this is equal to this. If this guy was 0, then we know it also has to vanish at Tj, at t, so it would be identically 0. So this is t. Okay, because the Jacobi field, because this guy is minimizing, it has no conjugate points from Tj minus 1 to t. If this value was 0, it has to be 0 at t also. It would be identically 0. So I don't want this to be identically 0. And now for t in this interval, let Vt be the piecewise smooth vector field along gamma t, such that V restricted to tk minus 1 up to tk is a Jacobi field along gamma restricted to tk minus 1 tk, sorry, Vt, which coincides with the notation here is a bit annoying. what am I saying? I fix this little v, right? Remember this space is T gamma T1 M plus T gamma Tj minus 1 M. Okay, so maybe I should call this SL, right? So VL. So V is equal to V1 up to Vj minus 1. Each VL is in T gamma TL of M. Okay, so I want it to be a Jacobi field along these guys for k equals 1 up to j minus 1, and such that Vt at t equals 0. So let me draw a picture. It'll make it easier to see what's happening. I haven't used that much color today. Okay, so let's draw. This is gamma of Tj minus 2. This is gamma of Tj minus 1. Gamma of Tj. And then our point T is somewhere between Tj minus 1 and Tj. So the vector field V that I'm taking, Vt, I'll draw a picture that like this is what Docarmo does. This is just emphasizing that. So this value here is V at Tj minus 1. We've prescribed the values at each of these points from 0 up to, I guess we want Vt at 0 to be 0, and we prescribe what it is at each of these gamma of TL up to j minus 1, and it's a Jacobi field, so it's uniquely determined up to here, and then we want it again. The Jacobi field which coincides such this, and V restricted to T j minus 1 up to T is Jacobi field such that it vanishes at time T. So it looks like this. Okay, so it's essentially that says that V is in Vt minus. Okay, it's a long way of saying it because I want to modify it now. That's what it means to be in Vt minus. Let Wt be the piecewise smooth vector field along gamma T plus epsilon, which is gamma restricted to 0 T plus epsilon. So the notation is a little strange, right? Because I'm calling it W sub T because it's going to depend on this time T, but it's going to be a vector field along gamma up to a little bit higher, such that Wt of S equals Vts for all S from 0 to T, and Wts is 0 for all S from T to T plus epsilon. And of course, this is piecewise smooth because we define, sorry, this should be an S. No, this is right, this is T. Because we define Vt at T to be 0. So this is piecewise smooth. And in the picture here, W is the same thing as V, but then it also includes this up to gamma at T plus epsilon. Okay, so it's equal to Vt until here. Vt is only defined until here, then we extend it by 0. So then It of Vt is equal to I T plus epsilon WT, WT, and this is because WT equals 0 on T plus epsilon. Okay, so this is the calculation we did a few minutes, like half an hour ago in step 1, in claim 1 to show that it was non-decreasing. We haven't used the index lemma yet. We're going to do that now. And this is strictly bigger by the index lemma to I T plus epsilon V T plus epsilon V T plus epsilon. And this is because V T plus epsilon is a Jacobi field along gamma T plus epsilon, and WT is not. So let's draw a picture to understand this. I'll draw another picture here. So we have gamma of Tj minus 1, gamma of T, gamma of T plus epsilon. I've got this is WT, right? It's equal to V up to time Tj minus 1, then it goes to 0. It's a Jacobi field, and here it's identically 0. And what's Vt plus epsilon? Vt plus epsilon agrees here, and then it's the Jacobi field from a Tj. Sorry, this is Jacobi field along gamma. This is Tj minus 1 to T plus epsilon. Okay, so from Tj minus 1 to T plus epsilon, this Vt plus epsilon is the unique Jacobi field, which has the same value as Vt here, and which vanishes at time T plus epsilon. Okay, so that's a Jacobi field. This one is not a Jacobi field because we know there's a unique Jacobi field with given boundary data joining two endpoints when there's no conjugate points. Right? So since there's no conjugate points, and since this is the Jacobi field here, this one is not the Jacobi field because this one's not smooth, right? And Jacobi fields are smooth. So the index lemma says that when you're looking at the index form, then if you put any two piecewise smooth vector fields that vanish at the two endpoints, then the index form for a Jacobi field is always less than or equal to the index form applied to any other piecewise smooth vector field. And the only time you get equality is if those vector fields are the same. But WT is not equal to Vt plus epsilon. That's why this is strict. So that's why we have a strict inequality. So this is the geometric content here. Okay, now we're almost done. Let's take that expression. So now let little v be in Sj minus 1 with IT VV less than or equal to 0. Suppose we have some vector v so that IT of VV is less than or equal to 0. Then let's give this equation a number. Let's call this sharp. It says that for sufficiently small epsilon, IT plus epsilon of VT plus epsilon VT plus epsilon is less than IT of VT, right? And what is this really? VT, maybe this is a better way to say it. VT is FT of this little v, right? And VT plus epsilon is FT plus epsilon of little v. That's more clear than what I was saying over here. So let's call this guy something else because it's not the same v, u. Then what does sharp say? says that IT plus epsilon, VT plus epsilon, VT plus epsilon is less than IT of VT, VT. So it says that translating translating back to the original language on SJ minus 1, it says that IT plus epsilon of VV is less than IT of VV. This is, sorry, let's do it in this order. Then this is true for all V in SJ minus 1. For all V in SJ minus 1. So I needed this. This is, yeah, the reason I needed this was so that WT is not equal to VT plus epsilon. Okay, but then this is true for all this guy such that Vj minus 1 is not equal to 0. Okay, and now I'm a little worried about that. We'll see how it goes. It's this guy here. That's what this means. This is V sub j minus 1. But I'm a little confused by what I've written here. So let's see how it goes. Okay, no, this is fine. So now, suppose that U in Sj minus 1 satisfies IT of UU is less than or equal to 0. Then we get that IT plus epsilon of UU is less than IT UU is less than or equal to 0. So why does this? I'm a little worried about this condition, but probably shouldn't be. Let's not worry about it now. I'll figure it out after the lecture, and I'll explain it. So if we have a point here on which IT is non-positive, then by this this inequality, IT plus epsilon will be strictly negative because of the strict inequality. Okay, so if IT is negative definite on some subspace S with the dimension of S bar equals I of T, then what we've just shown up here is that IT plus epsilon, for epsilon sufficiently small, is negative definite on S bar plus the radical of IT. Because remember, we're working now on a finite dimensional space, so we know that we can decompose into if we have this negative definite space, we can find a complement. We can write Sj minus 1 as some P plus S bar plus the radical of IT. This one is well defined. These are not unique, but there exists one, and the dimension here is I of T. The dimension of this is D of T, and then this is going to be the difference, right? It's going to be N J minus 1 minus I of T minus D of T. And so if it's negative definite, if we're in here, then with respect to this decomposition, it means that we're in here. Okay, so right. So if U satisfies this, that means U is in here. And this condition says that for T plus epsilon, the things that are in here now give you, the non-zero things give you something negative. So the index at time t plus epsilon is at least equal to I of t plus d of t, which is what we wanted to show, right? So claim 4 is proved. Modulo this issue that's confusing me right now about this condition. I suspect actually that I don't even need that condition somewhere. De Carmo said that and it was irrelevant. I'll check after class and I'll tell you. So we've shown also for epsilon sufficiently small, I of t plus epsilon is I of t plus d of t. Yep. These are both U's. Yeah, these are all quadratic. This is always the quadratic form. Okay. So oh wow, look at the chart. Okay. I might actually have to I mean, I'm going to finish the proof in the next 3 minutes, but I might have to leave the corollaries to next time. So now we've proved the Morse index theorem, because we know if this is the t-axis, we know what the function looks like. It starts out as 0, and then it makes a jump, and then it makes another jump. I don't want to make these look like they're the same size. Okay, so what is the index of IA? Well, it's going to be this value. But what is this value? I need to know how high I am. I started at 0, and every time I hit a conjugate point, whenever t is an interior, for all t that's between 0 and a, you see the reason we exclude a here is because this is continuous from the right. So for every t between 0 and a, where there is a conjugate point to gamma of 0, that's a time where it'll jump by claim 4, right? And it'll jump by an amount equal to d of t. So this is equal to the sum over all t in between 0 and a, such that gamma of t is conjugate to gamma of 0, and the amount that it jumps is d of t, which is the multiplicity of gamma of t. And that's exactly what the index theorem says. Okay, so I have three corollaries of the Morse index theorem, but because I only have a few minutes, 2 minutes, I'm going to just state one of them now, the simplest one, and we'll do the other two on Monday. So corollary, that gamma, it's not a corollary of the statement, it's a corollary of the proof that we gave. Let gamma be a geodesic, then the number of the set of conjugate points to gamma of 0 along gamma is discrete, and hence there exist only finitely many conjugate points. Okay, and the proof, this is a corollary of the proof of the Morse index theorem. It's claims 3 and 4, right? The only times that this index changes is at a conjugate point, and every time we have a conjugate point, there's some epsilon on both sides where it's not jumping, right? It's constant here from the left, except that it doesn't have a limit. The limit is not the same, and it's constant here from the right. That means every time I have one of these, there's a neighborhood of which there's no more. Okay, so it's a discrete set, and then I have a discrete. Is this right? What I said? I can't have a discrete subset of a compact set that's infinite, right? So it's finite. Okay, so next time, two more, but really one is just a contrapositive of the other. Two more corollaries of the Morse index theorem. And one is called the Jacobi theorem. But it's essentially what you're proving in problem 1 of assignment 4. You're proving that after the first conjugate point, your geodesic will never be minimizing. Okay, so it's a more fancy way of stating that statement as a corollary of the Morse index theorem. And of course, you don't have to use this to do problem 1. That's very, very basic. I give you all the hints on how to do it. And then we'll start chapter 12, which is Priceman's theorem. Priceman's theorem, as I said at the start of the lecture, tells you something about a compact manifold with a metric of negative sectional curvature. It tells you something about the fundamental group. So that's the plan. We have 3 more lectures. I will figure out this business here that's bugging me this afternoon, and I'll let you know on Piazza.